Welcome. This season, we're going on a journey. We're going back to the very beginning of the modern story of machine intelligence.
We are. We're exploring the foundations of natural language processing.
Right, because to really understand the giant language models we rely on today, you first have to see what came before.
The decades of breakthroughs, and just as importantly, the limitations that pushed the science forward. It's really the missing manual for modern AI.
What's so fascinating to me is how long researchers struggled with just the first step.
You mean, how to even represent human language?
Exactly. How do you take something so messy and symbolic and put it in a form a computer can actually work with?
It was this massive, sustained effort. And the first attempts, they weren't neural networks at all.
Not even close. They were based on statistics and some pretty simple assumptions.
We're talking about the classical foundations here. Things like bag of words.
Which is pretty much what it sounds like, isn't it? You just throw all the words from a document into a bag.
Right. Grammar, word order, all that just goes out the window. And from that simple idea, you get these really clever techniques like TF-IDF.
And that allowed early search engines to figure out which words in a document were actually important.
It did, by basically penalizing common words like the or a, and boosting the ones that were more unique and descriptive.
But that leads to a fundamental problem, just counting words that can't ever really capture what they mean, can.
It can't, and that was the wall the field hit. In that model, the word dog and the word canine are just two completely unrelated things.
They have no shared meaning.
None at all. And that rigidity, it demanded a foundational change in how language was represented.
And that change, that rupture, was the rise of word embeddings.
This was the great conceptual leap, the move to what we call distributed meaning.
With systems like Word2Vec and GloVe.
Exactly. Instead of treating a word as a single isolated symbol, these systems turned every single word into a string of numbers, a multi-dimensional vector.
And the core idea is that words that appear in similar contexts should end up with similar vectors.
That's the magic. It allowed for a kind of mathematical reasoning about language.
This is where we get the famous example, right? Where you can take the vector for king,
subtract the vector for man, and add woman.
And you land incredibly close to the vector for queen.
For the first time, a machine could capture relationships, these subtle gradients of meaning. It was the first true handle on semantics for neural networks.
So once you could model meaning, the next great challenge had to be sequence.
It was. Language isn't just a bag of words, it unfolds over time. Meaning depends on context from sentences ago.
Which brings us to architectures like recurrent neural networks, or RNNs.
And their more sophisticated cousins, LSTMs and GRUs. These were the first serious attempts at modeling that flow, at giving the network a form of memory.
I've heard LSTMs described as having these internal gates.
That's a perfect way to put it. They could conceptually decide what information to remember and what to forget as they moved through a sentence. It was a huge step forward.
But they still had their limits. They process everything one word after another in a line.
That linear constraint was a real bottleneck. They struggled with truly long-range dependencies context needed from paragraphs away.
And that bottleneck leads us directly to the ultimate turning point in this story.
It does. The 2017 paper, Attention is All You Need.
The question became, why force the model to read word by word?
When you could let it look at the entire sentence all at once.
And pay special attention to the words that matter most for a given task.
That's it. Attention gave the model a way to weigh the importance of every other word when processing a single word. It created direct connections across the entire sequence simultaneously.
A vastly more powerful way to model language.
And that one insight, that mechanism, is what gave us the transformer architecture.
The architecture that underpins virtually every foundation model we use today.
So today's models aren't some sudden magical leap. They stand on the shoulders of this slow, cumulative journey of ideas.
Ideas about meaning, about sequence, and about context. Understanding that history gives you a real intuition for why the breakthroughs of the last few years could even happen.
The field had been preparing for this moment for decades.
We hope you'll join us this season as we unpack that story, the foundational journey that shaped our world.